Okay, the first thing I think is to get out of your mind this idea that iron filings are somehow childish or toy. Now, after all, this idea of using iron filings was thought up and used by Michael Faraday, the inventor of the world's first electric motor. So, you know, I think that's the first rule. Get out of your mind anything to do that this is childish. We're doing childish things here. No, this is a tool, just a technique for having a look at lines of magnetic force, or field lines, magnetic field lines. So basically that's all that is. That's just, I suppose, mental stage one. You're going to do some work, you're going to have to use some iron filings because you want to be able to see roughly what's going on with the lines of force. Because once you can see something, well, you can have a better idea of what's going on and understanding, and then you can start to, you know, change things, manipulate things. Say, oh, well, what if I do this? Let's see what happens. You can actually see things with this. So that's the first step. Okay, the other thing we'll start on is, you may not have seen this at school. So when I was at school, I used to like permanent magnetism. Most kids do. So, you know, whenever I find a book on permanent magnetism, I read it voraciously, you know, from cover to cover. There weren't too many out there on permanent magnets. There was lots and lots on electromagnetism, packed with gross, awkward equations, and mainly not too graphical, I would say. You know, as I say, if you really understand something, you should be able to, you know, have some sort of graphical representation of the equation, and so you can actually see what it looks like. So once you can see something, you can start to get your mind around something and work with it. But not when it's just like a whole load of maths with no graphical, three-dimensional or better, you know, representation associated with it. You know, on one page you've got the equation, on the other page you've got a, you know, some sort of diagrammatic representation of the equation. I'm always suspicious about books that don't show some sort of graphical one-to-one correspondence sort of thing. Anyway, so of course in Newton's day you didn't have these super duper or Tolkien magnets or Tolkien glue. Yes, there's a joke in there for you, for the nerd world. Basic concept of permanent magnets, of course, you know, opposites attract, likes repel sort of thing. Okay, nothing too special about that, but I'll show you something they probably didn't show you in school. They didn't show it in my school, wasn't in the books. So I'm going to call it my effect because, as I said, I used to read these books voraciously and it was never mentioned in those books. Maybe it's been mentioned since, so maybe someone else has discovered it. I don't mind. That's what science is all about. I'm just here to tell you something I've noticed that's very simple, very subtle. And you'll see online, I've done this with rulers, so I've gone from the qualitative to the quantitative. And it basically seems to be just a recapitulation of Newton's third law, which is to every reaction there's an equal and opposite reaction. In a direct parallel to back EMF and things like that, which is, you know, to do with electromagnetism, which there is a lot in books about. Okay, so we've got this repulsion that, you know, they keep roughly the same distance. That's not the good bit. Now the good bit is when you put this one up to there and hold it, either with your fingers or you super glue it together. See, something they didn't have in Newton's day. It didn't have Tolkien glue in Newton's day. You wouldn't have someone holding this thing for, you know, half an hour or something. But anyway, now you'll find that the field strength has gone down. You know, so you can do this with any magnet, any of these sort of magnets. It works with even the new ones, the neodymium iron boron. Now, simple effect, but it's very subtle, very simple, easy, very reproducible, works all the time. You can take your measurements don't change with your ruler. You can see them online. But it helps you to get around the gating problem, which we'll show in another video soon. You can actually show that you can negate the gating problem down to a minimalist level where it doesn't become a problem, and where momentum can take over, can overcome. You can actually reduce the gating problem down to a minimalist situation where momentum can overcome it, sort of thing. Yeah, so you don't actually totally get rid of it, but you've minimized it so much, you've taken the limit on it basically, so much that it isn't a problem anymore. And that's a powerful tool. So a simple idea like this can then be adapted and used in a practical situation where other people are having problems. Or if you look at them on YouTube, they're having trouble with this gating, they just can't get their heads around. Well, the first thing you've got to realise from this is the only answer is repulsion. Attraction, you're not going to do it with attraction, you can only do it with repulsion. So that's the important step. Now, and if you put this over with iron filings, you can see the way the field changes as well, but I'm saving that because I'm going to show you my next stage, which is how it works in the practical real world. But the next bit I wanted to get onto was this idea is magnetism another form of radioactivity? It's a bold thought, I know, but let's look at the rough evidence, you know. Magnets, you know, you magnetise them once and you can stick them on your fridge. They take force to pull off, but they can sit on your fridge for years, you know. They do lose their strength over years, you know, 30 years they start to lose their strength. Gives the impression of a log function, losing their strength over time. Let's look at the other evidence. Most of the permanent magnets either have two or more massive elements and then a small one, a little tiny one. So you've got like alnico magnets, so you've got big nickel, big cobalt and a smaller aluminium. You've got neodymium iron boron, you've got the big iron, much bigger neodymium, and you've got this small boron in comparison sitting there. You start to see patterns, trends. I mean, this is what science is all about, looking for patterns and trends and, you know, parallel lines of information and comparing one to the other and things like that. That's what we do in science. We notice these subtle things, you know, saying, oh, you know, big atoms, sort of logarithmic decay of magnetism over time. You can say, oh, they're being knocked over time, it's the vibrations in the ground, it's the earthquakes. You can always put these in a double gimbal fluid bottle or something like that, do a long experiment like the coal tar experiment over 100 years, but have we really got 100 years to wait? We need the answer now. There's people over in CERN trying to get a sun on Earth, and you know what? Truth is stranger than fiction. Something goes wrong over there at CERN. You've just wiped out all the best minds in the world. Well, most of the best minds in the world. I'll grant you that. So yeah, I don't really think we really want to have a sun on Earth, this close to the Earth, in case something goes wrong. Do you? Anyway, that's the first of this. Yeah, I'm in a laconic mode today, so I'm sorry. Forgive me for that. But when you see the next bit, you'll think, oh, okay. So we'll go on to the next bit now.